Okay, 3 tasks. What was the order of difficulties first? I would say that, at least for me, P3 was easiest to start. So I immediately got some observations, then it's implementation. But still, in my opinion, P3 is easiest. Then maybe it's P2 and P1. But I think people disagree heavily about it. I saw discussions in Discord, and every problem had some people saying that it's the easiest one. As I was saying yesterday a little bit for bronze and silver, your strategy should be not to focus on one problem because you don't know which one is the easiest. We will do them in order, starting from hoof, paper, scissors, triplets. Do I have similar problems? Yeah. So like before, I will show you some Euler mixtures. There are a few similar problems out there, including this one. Also including Baltic Olympiad mixture, which I think has the same problem, but it's hard. And there is also ICPC problem, 3 kinds of dice. ICPC. No. So it's here the task C. I also know one problem from Polish ICPC stage. So generally, there are a lot of similar problems out there, especially in ICPC, and it is beneficial if you have solved at least one of them. If you did, then solving this is very reasonable. And if not, then solving this is very hard. I pasted into Zoom chat. Please somebody copy it into the YouTube chat if possible. We have a game of, let's say, rock, paper, scissors. Every player has some probability of playing rock, playing paper, playing scissors. For 2 players, we wonder which of them wins more likely with the other. And then we want to count triples such that first beats the second, second beats third, and third beats the first one. So for example, one person might have a probabilities of playing rock, paper, scissors 0.2, 0.45, and 0.35. This is rock, paper, scissors. Paper beats rock, rock beats scissors, scissors beats paper. And somebody else might have other probabilities. Let's just say that those are some values. Do I want to use A? Let's say X. X1, Y1, Z1. There is a second person with X2, Y2, Z2. And what is the probability that this person beats this person? Say that this thing beats that thing. Probability X1 that first person plays this times this probability minus, or maybe that plus Y1 times Z2 plus Z1 times X2. We compare this. This is probability that first person wins. We compare this with similar probability of when does second person win. X2 multiplied by Y1 plus, and so on. Something plus something. Already when you see this, you should think about geometry and cross product, but it's not quite there. If it was just simpler, comparing this to summation of 2 other parts here, it would likely be cross product, but it's not. It's the sum of more values. And I'm not even yet solving the problem about triples. I need to understand the logic of this, or the intuition behind this, how to equivalently, nicely understand when one triple beats another. Now, There are different ways to proceed from here if you have not solved similar problems before. The first thing you can do is try to visualize, or use online tools for that. You can try to visualize the triples of points. Generally, when you get 3 points, sometimes it's three-dimensional geometry. So I will say here 3D geometry. This is not a good way to proceed. I'm just telling you a possibility. We know that the probabilities sum up to 1, so we know that they belong to some kind of triangle. And we are given a lot of points on this triangle, and we wonder what points beat some other points. In particular, we know that the point in the middle, there is this nice point 1/3, 1/3, 1/3, which in rock, paper, scissors, I think almost everybody knows, this is a balanced strategy that cannot be beaten by any other strategy. This thing ties with everything else. There is nothing else that can beat it on average or can lose it to it on average. Everything else in this triangle can be compared to each other, and mostly something is better than the other. Whatever is more towards rock will beat what is more towards scissors, roughly. So one possibility is to think about this triangle with the middle here, and if every vertex is rock, paper, scissors, you can roughly figure out that whatever is more towards scissors will beat whatever is more towards paper, and you will roughly figure out that this point beats whatever is in this area, and eventually from some math you will figure out the formulas required to solve the problem. But I think it's not very easy to do it this way. What I will do instead, again, but without knowledge of those other problems, is I will do the following observation. If my strategy of playing is, let's say, what did I use? 0.2, 0.45, 0.35, let's say, for rock, paper, scissors. If I try to compute my probability of beating somebody else, I claim the following interesting observation. If I decrease my probabilities by the same value, so I decrease everything by 0.1, then, and now the probabilities do not sum up to 1, so let's say that with probability 0.1 I play rock, with probability this I play paper, with this I play scissors, and otherwise there is a tie, or I don't do anything, whatever. Turns out that no matter how you define it, this is equally good strategy. Why is that? Because no matter what let's imagine that your opponent generates their random move first, and your opponent, you don't know about it, but they play paper. By how much you changed probability of winning when you modified your triple from this one to this one? Well, you decreased probability of rock, so losing by 0.1, and you increased probability, decreased probability of scissors by 0.1. So the win probability decreases by 0.1, loss probability decreases by 0.1, so the total is the same. Also, if you analyze this formula, where we multiply this thing by this one, but we subtract this thing by this one, you will see changing one triple down by 0.1 doesn't change the result of this comparison. I can go further with that. I can decrease everything by 0.2. So I claim that no matter what your exact math is, those formulas that we listed, the result of the math will be the same if I decrease everything by the minimum and I obtain a strategy that doesn't play rock at all. I claim that this strategy is equivalent to the strategy that plays paper with 25%, scissors with 15%, and it does nothing with 60%. Does nothing means there is a tie. Because that nothing strategy was equivalent to the 0.2 per each category probability, which is balanced. It's part of the balanced strategy of playing rock, paper, scissors, one of them at random. And now from 3 values, we are down to 2. If now in the input, every triple would have the same position as the minimum, like rock was the smallest of 3 numbers, we would be very happy already because we would simplify 3 numbers per triple into just pairs of values. Turns out I can go a step further, and the math still works if I decrease it more and I go into negative values. So I can, for example, subtract 0.35. So if I subtract 0.35, I will get this, and 0. I claim that this is still strategy that has the same results, if you do the math, against any other strategy. I subtracted the 0.35 per each category probability, which is a balanced strategy, so on average it ties. I can compare this with every other strategy. It doesn't matter that those probabilities in real life, they don't make sense. Formally, if it was a math problem and you tried to prove something this way, you would need to say that it's some kind of expected value of how much you bet. That I bet this much. So actually, I play rock with this negative probability. It's very strange to define it this way. We will not go there, but I think it's doable. Still, let's pretend that my probabilities are negative like this. So what I'm saying is for every pair, rock, paper, scissors, or every, triple, not pair, for every x, y, z, I transform this into x minus z, y minus z, and 0. And I focus on this, where nobody plays scissors. Nobody ever plays scissors. I just have a bunch of pairs of probability of playing rock, probability of playing paper. And now I want to count the number of like triples of competitors such that something. But for just 2 things, for just rock and paper, for just x1, y1, and x2, y2, just rock and paper, it's way easier to compute who wins on average. Probability x1 multiplied by y2, we compare against y1 times x2. So if I play rock, they play paper, let's say, and then paper wins versus the other combination. And if you put this to the left side of the equation, you have the cross product. So the solution here is that we first every triple transform into a pair like this, and then we can investigate cross products. And we have a lot of vectors, and vectors count triples of vectors such that something with cross product, which has very nice geometric interpretation of if you have those pairs, then one cross product is smaller than the other, or is smaller than 0 if one vector is to the left of the other. So for A, it wins against everybody here and loses against everybody here, which means we are counting triples of points such that B is to the left, to the right of this line, and C is to the left of this line, which roughly looks like this. So one way to phrase it, count triangles where point 0, 0 is inside. Another way is count triangles such that they are on in one half plane of the 0, 0. And those are the bad triangles. So this means A wins with, here A is to the left of C, C is to the left of B. So A wins with C, wins with B, A wins with B. This is not a pair that you want to count, or not a triple. This is a triple that you want to count. In this the top drawing, we have A smaller than B, smaller than C, smaller than A in terms of cross products. And for that, you need geometry knowledge. You need to know how to do it, and it's a quite standard task to do it. So also, I told you about this 3D. What we did here with simplifying triples is in some way equivalent to projecting points into the plane we are looking at this plane containing this triangle, the plane x plus y plus z equals 0, and we are projecting every point into this plane, so we would only have two-dimensional problem, where this third point here becomes 0, 0, and then it's the same. But the easiest way is to just already be aware of the technique that we can do this transformation. That's what experienced competitors could do in this problem. Just skip all this logic, all this guessing or figuring out, and just know that this is what should be done. So finally, how to solve this geometric problem? You are given endpoints, x, y, count triples, A, B, C, such that in terms of cross products, we have this. The smaller means that cross product of A and B is negative. You can do that by sorting by angle and then using two pointers. And I still recommend that you instead count bad triples. So count such triples that, for example, A smaller than B smaller than C and A smaller than C. I would prefer to count those and then subtract from entries free. That's way easier. Count this and subtract. In all this logic, we need to be careful with collinear points as well. Collinear are always bad. So whenever we have a point here A and collinear point here B, those two strategies are equivalent. They are tying with each other. So this is a tie. Also, if it was on the other side, it would also be a tie. So such pair with anything else is a tie. We can count, I would count it maybe as a separate variable. So you want to take care of this. And also for every point A, you want to know how many points are in this half plane. If the number of such points is C, then for this point A, there are C choose two pairs of the points here, where each of them with me forms a bad triangle, a bad triple, such that this happens. Because, yeah, we can sort them. The 3 points that are in one half plane, we can sort by angle with respect from the point 0, 0. So we sort the points by angle. We use two pointers, because if points are in order, like 1, 2, 3, 4, 5, and so on, 8, 9, 10. When you get to point 2, you want to know the opposite point, like 8, because if you know that we have this angle, we have this angle here, that 8 is now, or maybe better, we have 2 and we have this 7 here. 7 is the last point that is in this same half plane as a 2. Then 7 minus 2 is 5. 5 is the number of points here. So 5 choose 2 is the number of here pairs that create bad triangles with 2. You just need to be careful with collinearity. So 7 should be the last point that gives you, let's say, strictly positive or strictly negative, sorry, cross product if you compare this versus that. And also, if there are a lot of here collinear points, you should process all of them at the same time. And you want for all of them to know how many points are here. And the number of them, for each of them, add to the answer this choose to. Not to the answer, to the number of bad triangles. Every bad triangle will be counted once, because it will be counted from the perspective of angle-wise first point. But be aware that here you also count triangles that look like this. There's this point, and then here two collinear things. You're counting those, which means in that implementation, we need to be very careful. If I could spend 2 hours to maybe discuss all the Platinum problems, then we would discuss similar things. We would discuss maybe implementation, taking care of those collinear things. But we don't have that much time, so I will leave it like this. Time complexity is n log n. For somebody at platinum level, I would expect that you may possibly not come up with this transformation, but once you get to 2D, you need to be able to solve this. Otherwise, you're lacking in geometry skills. Tell me if you have questions. If so, I will try to answer.